Okay, thank you. I want to, this seminar, first of all, I want to thank you for the presence here. This is the third specialized seminar at the Institute of Geology in this new format. And this time we have invited Professor Brice Hoover from NASA. Brice Hoover is a physicist. He graduated in 1964 or 63, and beginning with 1966, with NASA Marshall Center Field Project. His specialty first was solar physics, and then passed to the astrobiology. Last time, that means few decades, he participated in a lot of expeditions in Antarctica and Siberia, looking for fossils and for extremofilelor, because it's the major position. If the life was developed in other planets, it is possible to get more information about the life condition investigating extremofilelor. Also, he is very interested and investigating a lot of meteorites, which presently show inside different formations which could be attributed to fossil life. So this theory, the theory of panspermia, which should be proved, can be proved by showing that meteorites are the best transporter of the elementary form of life. So Richard will present us today its a lesson, a seminar on the microfossils which has been discovered in meteorites and how can be considered as a form of life transport in the cosmic, in the space. My name is panspermia. Richard, thank you. Please, it's your.
Thank you very much. It's indeed a pleasure to be here in Bucharest and have an opportunity to discuss this research with the group that we have here of scientists and geologists, paleontologists. The problem that is a very, very important and interesting problem is the origin of life. Where, when, and how life originated is truly one of the greatest unanswered questions of science. There are two basic paradigms that have been involved in this problem with the origin of life. The endogenous paradigm is that life on Earth originated on Earth, and that is widely accepted across the entire globe. There has also been an exogenous hypothesis that was started back in the days of the ancient Greeks, that life originated elsewhere and was transported to Earth throughout the cosmos. This is the concept of panspermia, seeds everywhere. That was advanced by a great number of scientists, most recently by Professor Sir Fred Hoyle and Chandra Wickramasinghe, but of course Gustav Arrhenius, back at the beginning of the last century, made profound contributions to the theory of panspermia. The presence of microfossils in carbonaceous meteorites provides definitive observational evidence of the existence of extraterrestrial life. And if life exists beyond the planet Earth, then we must consider the possibility that biology may have been transported to Earth from comets, bodies such as wandering or rogue planets, icy moons, and so forth. For the last quarter of a century, I've been doing scanning electron microscopy of carbonaceous meteorites. And within the last 10 years, I did neutron activation analysis studies in collaboration with Marina Fontosieva at the Joint Institute of Nuclear Research in Dubna. And there have also been very exciting new discoveries made by space probes that give rise to interesting observations that suggest that this new mechanism for transfer of biospheres should be considered seriously. The fundamental problem with the origin of life on Earth is that recent studies have shown that simple cells just simply do not exist. Here we have an example of the DNA gyrase enzyme, and here is the human genome, which is 3.2 billion base pairs, and in this microorganism known as Polychaos dubium, we have a grand total of 670 billion base pairs. So the genome of Polychaos dubium is vastly larger than the human genome. The other thing that is most interesting is here we see a transmission electron microscope image of a bacterial flagellar motor. That could have easily been designed by Nikola Tesla or by Thomas Alva Edison, and yet it was designed 3.2 or further billion years ago. And you see the same characteristics that you have in ordinary electrical motors, but note that this is a 20 nanometer bar. So if you were to ask the scientific community, build me a functional electric motor with no greater than 40 nanometer diameter, they would find this to be a profoundly difficult, nay I say at this present time, a totally impossible task. Sharov did some very interesting studies in which he looked at the timeline by linear regression of genetic complexity, and when he looked at various kinds of life forms, starting with mammals and fish and worms, eukaryotes, prokaryotes, and he gets this kind of a line by linear regression analysis. And the fascinating thing is that if you extrapolate it backwards, it crosses the axis at about 9.5 billion years. Well, that's a fundamental problem because the origin of our solar system occurred about 4.5 billion years ago. And this kind of linear regression analysis suggests that life may have originated on a much more ancient body, especially if the paradigm of the endogenous origin of life is correct, and that is that amino acids rained down in ancient oceans, and then over a long period of chemical evolution, you finally got to the point where you had the first biomolecules, and then after you get the first biomolecule, you get the last universal common ancestor, LUCA, which was the origin of protocells that then evolved into all of the forms of life that we know today. The problem is, in the paleontological record, there simply is no evidence whatsoever of primitive protocells. And in fact, in the paleontological record, we see evidence that life began on Earth somewhere between 3.8 and 4.2 billion years, which means you had an onion skin time, 300, 500 million years maximum, for life to have originated. But for a big portion of that time, we were in a planet that was completely riddled with gigantic impacts of asteroids and meteoroids and enormous volcanic eruptions. So the Hadean Earth would have been a very, very difficult place for life to have gained a foothold. There are some fundamental requirements for all living things that we know. One of those fundamental requirements for life is water. Water is the most abundant compound in the entire universe. It comprises some 60 to 70% of the mass of all living cells. It's a very unique molecule. It has a polar bent geometry, and the HOH bond angle is about 104.5 degrees. Water, because of this characteristic, expands upon freezing. It's fortunate. If it didn't expand upon freezing, I wouldn't be talking to you, because in point of fact, there would be no life on Earth. The fact that water expands on freezing means that ancient oceans and seas and lakes and rivers freeze from the top down rather than from the bottom up. And the other reason that occurs is because water has a maximum density if it's fresh water at plus 3.4 degrees Celsius. If it's salt water, around minus 1.8 to minus 3. The difference depends upon the degree of salinity. But basically, you could say that since the water of maximum density is always going to sink to the bottom, the deeper regimes of all oceans and all freshwater lakes on the entire planet Earth is going to be 0 degrees C plus or minus about 3.5 C. Well, That doesn't just apply to the planet Earth. Physics is universal. The laws of physics and chemistry work the same way regardless of where you are in the cosmos. That basically means that every deep ocean on every body in the entire universe where there is liquid water is going to be essentially the same as the water underneath the North Polar ice cap of Earth, or water underneath the ice shelves of Antarctica, or water in the deep Pacific or the deep Atlantic under the equator. They're all going to be the same. They're all going to be dark, very high pressure, temperature 0 C plus or minus about 3.5. In addition to water, and by the way, water doesn't have to be in liquid state. I spent many, many years studying life in ice. Life exists in ice. In fact, there are more ice worms on the planet Earth than there are humans. It can be in solid, it can be in gaseous, or it can be in liquid state. You require a source of energy. That can be light, heat, radiation, organics, chemical reactions, and lithotrophic microorganisms live by basically eating rocks. So you have a wide variety of forms in which life can gain the energy for its biological metabolism. You require about 20 of the 118 chemical elements in the periodic table of the elements. Just a few years ago, academician Oganessian completed the periodic table of the elements by adding tennessine, neonium, moscovium, and the last element, number 118, is named Oganesson after Yuri Oganessian of the Joint Institute of Nuclear Research in Dubna. You can write a simple chemical formula for life. All cells, 90% of the mass of cells can be expressed as C4H7, O2, N1, PO.2, SO.1. Those basic chemical elements are essentially life. Now, we can add on to those 6 life-critical major bioelements some 14 others, and you take those 20 out of the periodic table of the elements, and you've got everything that is found in living cells. Cells are basically 75% water, about 15% of the cells are protein, and 6% is composed of the RNA and the DNA. One of the other absolute essentials of life that is not often talked about is this phenomenon of homochirality. Louis Pasteur was studying dregs of sodium ammonium paratartrate in wine dregs, and he discovered that the sodium ammonium paratartrate was optically active. It could rotate the plane of polarization of light. Well, the fascinating thing is that when Pasteur made sodium ammonium paratartrate crystals in a chemical reaction, it wasn't optically active. And he couldn't imagine why, but then he crystallized some of these crystals made chemically, and he found that even though they were identical chemically, they had a different chirality. They were like the left and right-handed glove. If you try to put your left-hand glove on your right hand, it doesn't work. And the same way with the chirality of chiral molecules. And in fact, almost all biomolecules have this phenomenon of chirality. There are a few that are symmetric that do not exhibit homochirality, but by and large, all of the biomolecules of life have this chirality characteristic. And that's very important because if you imagine a DNA molecule where you've got a right-handed helix and you have the ribose and the deoxyribose on the DNA, if you were to, and they're all right-handed sugars, if you were to stick in a left-handed sugar into that DNA chain, you're spiraling like this, and then you want to try to spiral like that, it simply wouldn't work. It would crash the DNA molecule, and therefore it would no longer function. One of the fascinating things is that homochirality is a signature of life. That was stated by Louis Pasteur, and it is indeed correct. The fascinating thing is that in carbonaceous meteorites, and indeed in the samples returned from asteroid Ryugu, we find that there is an excess of the L-enantiomer, the L amino acids. Some of them have an excess, and in fact, in the Tagish Lake meteorite, the aspartic acid has had an L-enantiomeric excess of the order of 60%. Well, you can't do that chemically. In fact, no one has ever been able to make, by any kind of chemical processes, amino acids with an L excess that exceeds more than a few percent. And you have to do that by amplification and various other techniques. And there are all sorts of theories as to how optical activity could be started by the polarized light, ultraviolet polarized light from supernovae and things like this. But basically, optical activity, homochirality, is a signature of life. It is made by biomolecules. And the fascinating thing is that in living things, in RNA, you have the Watson-Crick canonical base pairing, in which adenine pairs with uracil and guanine pairs with cytosine. In DNA, the uracil is replaced by thymine, and adenine pairs with thymine, and guanine still pairs with cytosine. Well, in the carbonaceous meteorites, we find some of these nucleobases, but we don't find all of them. And that's a very, very important aspect of this story, because a lot of people try to criticize the work that I've been doing by saying these are modern biological contaminants. Well, I submit to you that that is verifiably false, because if you put in ordinary bacteria, cyanobacteria or diatoms, in a carbonaceous meteorite, I submit to you, you will put in all 5 nucleobases, and you'll put in exactly the same amount of guanine that you have of cytosine. So the absence of cytosine, while guanine is readily present, proves that it is not the result of modern biological contamination. Again, these various biomolecules are essential. The amino acids exhibit these characteristics, and then they form the peptides, and so you get these long-chain polymers. Many years ago, a Russian scientist by the name of Sabita Brizov was arguing that there would be life in deep ice above Lake Vostok. Mshinetsky at the Institute of Microbiology kept being pestered by Sabit, and he decided the best way to shut him up was send him to Antarctica and let him try to see. So Sabit went to Vostok Station, and he wintered over more than once at Vostok Station in Antarctica, drilling in the Antarctic ice. I think he's the only human being ever to wintered over at Vostok Station on more than one occasion, because the temperature there during the winter can get down to -85, -90, with 90 to 100 kilometers per hour or more winds. You can die outside of the station in literally a matter of minutes. But Sabit found in all of these ice cores that he drilled at Vostok Station, there was biology in the cores. Microorganisms, mainly in the form of microfossils, but all the way down to about 2.4 kilometers, the microorganisms, many of them were still alive. And they had been cryopreserved in the ice, frozen in the ice for hundreds of thousands of years, and still living. This picture in the center shows one of our electron microscope images of diatoms. They're in your view, but you see here 2 complete fructils of diatoms. This was from a 2,827 meter deep core of Vostok ice. And then I spent a lot of time studying the Fox Permafrost Tunnel in Alaska. There you walk back into the tunnel, and you're walking into the Pleistocene. There are roots of trees that lived and died 32,000 years above your head. Pleistocene steppe bison, Pleistocene woolly mammoth tusk sticks out of one wall. It is absolutely walking into the Pleistocene. I have to say, it contains fascinating things like these moths that I have here. Those were taken from the Pleistocene of the Fox Permafrost Tunnel, and they're growing. So those mosses have been alive for 32,000 years, but just frozen and waiting for some very pleasant gentleman to come along and rescue them. I spent a lot of time studying life in ice. NASA would have had a fit if they had seen this picture. I was standing on an ice ledge and collecting samples out of this wall by driving a stainless steel tube into the wall to extract the ice from near the surface of the Matanuska Glacier. And one of the things that I want to point out, you see this little stream here, that's about a 6-inch diameter column of water streaming out of the glacier itself. And it makes a tremendous roar because it comes down about 200 meters, and when it gets to the bottom down here, some 200 meters below, is the Matanuska River. I was careful not to fall in, because if you fall in and will land into the Matanuska River, the chance of climbing out is rather slim. but I had to get my samples. So when I had examined this and concluded that the shelf there was going to survive it as long as I wasn't stupid enough to fall. This is Jim Lovell. I had the opportunity to go with Jim Lovell. I know when Gary, Jim was on Apollo 8 and the Apollo 13 missions. And we went to Antarctica in 2000. Got to sleep in a tent in Antarctica. Feet only a few inches away from my nose, but it doesn't matter because nothing smells in Antarctica. Your nose just simply refuses to work. This is in the Schumacher Ice Cave in Schumacher Oasis, and there's one of the 20 meteorites that we found on the blue ice of Antarctica. That is beautiful because all you have to do is go around on a snowmobile. You see a black rock. You stop and examine if it has these curved surfaces. You collect it, especially if it looks like a meteorite. We wound up bringing 22 samples back, and 20 of them were meteorites. In this ton of ice sculpture here, I collected a sample, and we found that contained a new species of bacteria that we named Sanglobacter gelidostatiaria from ice sculpture. This was my transport, a Russian tank called the Getate, which is not the most comfortable thing to travel in. We drilled through 10 meters of ice in Lake Untersee, and in that regime we brought up samples from 90 meters below the surface of the ice, and Dr. Kakuta was successful in isolating this new organism, which turns out to be a new species, new genus, and new family of bacteria that we named William Whitmania. We wanted to call this William Whitmania dandelioni because these long things with a puffball at the top look just like the weed that we have in our gardens called a dandelion. But the editors were sticklers. They insisted that we could only use Latin names for genus and species, so we decided, okay, we'll call it William Whitmania terrazaki, that being, of course, the name for the dandelion in Latin. There's always more than one way to get around a referee. There are interesting things with regard to the icy moons of Jupiter. We know that the icy moons of Jupiter have liquid water oceans, particularly Europa and Ganymede. The Jupiter Icy Moon Explorer is getting ready to launch, possibly, I think even today, maybe the launch date for JUICE. It's an ESA mission to go to the icy moons, particularly Europa and Ganymede. But one of the fascinating things is that on the surface of Europa, you see the blue ice and the white snow-like material and these deep red, almost purplish lines. Well, according to the scientific community, those are tolons. I don't believe it. I believe there's a very real possibility that they're bacteriorhodopsin-type pigments similar to these. This is a photograph taken at the bottom of Lake Untersee. Divers went in, Dale Anderson and Michael Story-Lombardi went underneath the surface of the ice through this 10-meter deep hole in the ice and swam and collected samples of these stromatolites, which contain cyanobacteria, Formidium, microcoleus, typical kinds of cyanobacteria that I find in meteorites. But you notice here they're red in color. This is our Myonotis nucleusii of Ludwig Kurtz that she discovered 3,042 meters down in the Greenland ice core. One of the fascinating things is these red colors, I think, are caused by pigments. I thought, well, perhaps there's some kind of minerals, and I went to the Keck Museum. I've gone to mineralogical museums all over the planet looking for red water-soluble minerals, and you can find salts that are red, but those are caused by bacteria that have the reddish pigments on the inside of the salts. And I know you have a wonderful array of beautiful minerals here, and I would like to know if any of you know of or have ever seen a red water-soluble mineral, things like cinnabar and so forth, and all of the beautiful silicates that you get in different shades of red are nice, but they're simply not water-soluble. And in fact, if these colorations were actually caused by water brought up from the ocean, and it deposited these kinds of intense red colors in the crevasses when the water breaks through the ice, then the Jupiter, the Europa water underneath this ice would have to be pretty much blood red, almost like it was made of blood, and that seems a far-fetched idea because, of course, the great red tides are not made by chemicals, but rather by microorganisms like dinoflagellates and red-tinted cyanobacteria and so forth. Many years ago, Tommy Gold, very famous colleague of the late Sir Fred Hoyle, and Tommy Gold also has passed away, but he wrote a book called The Deep Hot Biosphere, in which he argued that deep within the crust of the Earth, there would be biology, and it would be living in deep hot rocks. This was ridiculed. The scientific community knew this was absolute nonsense, but we now know it isn't nonsense because this is Desulfurotus audax viator, the deep microorganism. And fairly recently, about 5 years ago, the group from Spain, who were drilling in Rio Tinto, doing explorations of life deep underneath the rocks at 600-meter regimes, they discovered something very fascinating. They discovered cyanobacteria living in the deep rocks beneath the surface of the Earth at Rio Tinto. 600 meters down, there isn't a lot of light. These cyanobacteria were not afraid of that. They're not photosynthetic cyanobacteria, although they're the same genera and species as the photosynthetic cyanobacteria. They're just doing hydrogenotrophy. So the little guys say, okay, no light. Well, we got hydrogen, let's eat. So one of the fascinating things about life is we find it is more amazing than we could ever imagine. And one of the interesting things is in these deep rocks, you have the enthalpic reactions in which phosphorite and water combines to form serpentine and brucite, and phaolite and water forms magnetite, silicate, and hydrogen. Well, I find that most interesting because serpentine and brucite are found in the Orgite meteorite, magnetite, silicates, these various products of these kinds of chemical reactions of serpentinization, which produce energy, which yield energy, are found in the deep, in not only the deep rocks and the water mineral boundary in oceans, but they're also found in carbonaceous meteorites. Heat-producing elements are most interesting. We had the space race with the Soviet Union many years ago, and the Russians beat the United States of America to launching Sputnik, the first Earth satellite. This caused a panic within NASA, and Werner von Braun was brought in and asked how long it would take him to launch an Earth satellite. He said 6 weeks, but they already had one built. His handler said, no, let's say 3 months. So exactly 3 months to the day after Sputnik 1 was launched, Explorer 1 was launched on January the 31st, 1958. Then we started this great program to try to send astronauts to the moon. The Russians were working feverishly to beat the Americans in sending astronauts to the moon, but their large rocket had an explosion in early July. They say it was unmanned. I think it's probably more logical that they would have been planning to send astronauts to the moon because they knew precisely when our Apollo 11 mission was going to be launched. But in addition to that, after the moon mission was sort of winding down, there started a deep interior quest of the United States against the Russians. And one of the fascinating things is that the Russians were drilling the Kola super deep borehole in the Kola Peninsula. They started in 1970, and by 1994, when they finished, they had reached the depth of 12.3 kilometers. Amazing, amazing work. And throughout their cores, they brought up mud material, the broken rocks, and it was full of water. It contained hydrogen and helium, and astonishingly, biology. So, how in the world would that be possible? Well, we now know the deep crustal rocks of the planet Earth support an enormous amount of biology, and calculations indicate that there may be more biomass in the deep crustal rocks of the Earth than above the surface. So most of the biology of planet Earth probably lies beneath our feet.
But one of the fascinating things is that these rocks in the upper layers of the crust are primarily granite-type rocks, and those granites contain high concentrations of potassium, uranium, and thorium. That's one of the reasons why it's probably not a good idea to have a kitchen with enormous amounts of granite, because the radioactivity of those radiogenic elements can give rise to radon gas, and so you can be putting radon in your kitchen if you like to have lots of granite. But you also find granite coming up from the earth, especially when you have thick layers of radon coming up from the earth, especially when you have thick layers of granite fairly close to the surface. And it's caused by the radiogenic decay of potassium, uranium, and thorium. And the fascinating thing is that potassium-40 has a 1.2 billion year half-life, uranium-238 is 4.5 billion, and thorium-232 half-life is 14.2 billion years. Well, now with the Earth only 4.5 billion years, we have only gone through a couple or so of half-lives of the potassium, but only one of the uranium, and not even a single half-life of the thorium. The fascinating thing is that when these radiogenic isotopes decay, they produce gamma rays and antineutrinos, and the interesting thing is that the Earth is actually an antineutrino star. It is emitting more antineutrinos than it is receiving from all the rest of the cosmos. And in fact, antineutrinos have such an incredible penetrating ability. If you wanted to make a camera and use a shutter to stop all of the antineutrinos coming in like you do in an ordinary visible light camera, your shutter made of lead would have to be of the order of 4 light years in thickness in order to stop all of the antineutrinos. Well, the reason that is intriguing to me is because back several years ago, we started a project with Dr. Fontesieva. She has capability of doing neutron activation analysis there at the Joint Institute of Nuclear Research in Dubna. And here, I'm showing we got spectacular results for all the elements, particularly rare earth elements and heat-producing elements. But here I'm showing the heat-producing elements, potassium, uranium, and thorium, and also rubidium. Rubidium-87 has a much larger half-life of about 49 billion years, so it isn't really a major player as a heat-producing element on Earth because it has such a long half-life. It's almost stable, but it is radiogenic. But the fascinating point is, when I look at carbonaceous meteorites, and I look at these amazing stones called Polonnaruwa stones that were observed to fall in north-central Sri Lanka, the values here are typically 600, 900, 800. This is Giblet-Vincelbond CM2 of 1570. But here are all of the Polonnaruwa stones, and you see numbers ranging from, a couple of them there were only around 4,000 parts per million potassium, but many of them 150, 170,000 parts per million potassium. Enormous values. The same is true of the uranium and the thorium, just enormous values. And the Polonnaruwa stones are very, very exciting meteorites because they were observed to fall. They are extremely low density of 0.6 to 0.8. They'll float on water. There are only 2 rocks, to my knowledge, that naturally occurring on Earth that float on water, diatomite and pumice. These stones are clearly neither diatomite nor pumice. They have high porosity, similar to the dark boulders of asteroid Bennu, but they also contain a lot of beautiful microfossils that I'll show you later. In 1986, I had the distinct honor to work with the late Sir Fred Hoyle, who was the one who explained in detail the formation of elements within superhot stars. Fred Hoyle called me because he knew I had been working on diatoms for many years, because he wanted to talk to someone that could get him samples of diatoms. When he found out I was actually working in X-ray astronomy, he suggested that perhaps I would like to collaborate with him on a scientific paper. Well, being asked to collaborate with Sir Fred Hoyle on a scientific paper, it didn't take me long to accept that invitation. And we started working, and in 1986 we published this paper in Earth, Moon, and Planets, the diatoms on Earth, comets, Europa, and in interstellar space. And the fascinating thing is that when we look here at the spectrum of the Trapezium Nebula dust, between the Earth and the Trapezium Nebula, and this is between about, what do we got, 8 microns and 40 microns. We see all these nice little bumps and wiggles. The line is the diatoms, the dots are the astronomical data. The same here between the Earth in the 3 to 12 micron region, and we see all these beautiful agreements between diatoms and interstellar dust toward the center of our galaxy, which we now know at the center of our galaxy there's a beautiful gigantic black hole that has been shown in great detail by the Webb telescope. Well, we're not saying that these are diatoms. We're saying that they are biopolymers that are very similar to diatoms, and we argue that the ultraviolet and infrared data support a concept of a cosmic microbiological system in which diatoms or similar microorganisms might exist on comets, Europa, or in interstellar space. In 1806, the Alais meteorite fell in Alais, France on March 15th. That was the first known Ci1 carbonaceous chondrite that we have in captivity. In 1864, in the south of France, the Orgueil meteorite landed. And right now we have only 10 Ci1 carbonaceous chondrites in captivity. Several of them, the last 4, are from Antarctic meteorites. Berzelius started doing studies of Orgueil immediately, and he found that it contained water. He almost threw his sample out because he thought it was contaminated. Then he found others had studied the Alais meteorite and found that Alais contained water, and so we realized, well, perhaps it wasn't contamination, and we now know that it has indigenous water, as do all of the Ci1 carbonaceous meteorites. But indeed, it also contained organics, and in 1864, when the Orgueil meteorite landed, and was another Ci1 carbonaceous meteorite, Pisani and Klotz did studies finding carbon, water, and organics, and they concluded that the organics they were finding were similar to bitumen or to lignite coal. Well, coal is not produced by biology. All of the coal that we have on Earth is produced by biology. And they actually suggested that perhaps this was indicative that there was biology on the parent body of the meteorite. Well, one of the other things that was discovered, one of the scientists trying to find the density of the Orgueil meteorite took a piece of Orgueil, he measured the mass, he had a graduated cylinder, filled it to a certain level with water, dropped the meteorite in, and it immediately disintegrated. So he destroyed a beautiful fusion-encrusted meteorite. This all sort of lay dormant until 1962, when George Claus and Bartholomew Nage announced the discovery of what they considered to be microfossils in the Orgueil meteorite. This started an entire firestorm of controversy, and other scientists claimed, well, these were really not indigenous, these were contaminants of pollen grains, and in fact, they ultimately won the debate by saying that they had found a piece of Orgueil that had been intentionally contaminated. Someone had put in coal and bits of reed, and then they had glued the fusion crust back on by taking the powder and so forth and making it into a synthetic fusion crust. Well, before that 1965 paper was published, Palik actually published this image where she was a cyanobacteria expert, and she concluded that these were what she called blue-green algae. She saw cells, she saw a tapered filament with an apical cell, and after I started studying with scanning electron microscopes, I found exactly the same kind of structure in the Murchison meteorite, a tapered filament with a clear apical cell here, and most interestingly, right by the side of it, you see what is clearly an emergent trichome, and you can determine from here, this is a cell, that's a cell, that's a cell, so it makes it possible to measure the dimensions of the cells within the emergent trichome. The way many cyanobacteria reproduce is by the formation of trichomes in which an acridial cell forms in a part of the chain of cells, and that dies, and then this small chain of cells escapes from the sheath and starts replicating by mitotic cell division and forms an entirely new filament. and that's the way in which many of these cyanobacteria reproduce. This is an image of a form that was obtained by the great paleontologist Timofeyev at the Institute in St. Petersburg, and here I find a very, very similar form this was from his study of Miguel. This similar form was found in the Orgay meteorite by my own research. Close conducted a detailed chemical analysis, found ammonium and chlorine salts, potassium chloride, magnesium sulfate, magnetite, and here is his comparison of the Orgay meteorite, carbon, hydrogen, and oxygen with ring cool lignite coal. And you see what a very, very nice comparison. And it turns out that it is now well known that the dominant part of the carbon in the carbonaceous meteorites is in a polymeric form of matter, which is very similar to kerogen. On the 14th of May, 1864, at 8 o'clock in the evening, there was a giant fireball over southern France. Explosions occurred. Many of the people thought the world was coming to an end. They thought it was giant explosions. They thought it was an earthquake. Madame de la Pile thought her chateau was on fire. And she went to bed after the great excitement was over. And when she got up the next morning, as she was walking along her garden path, she found a white stone about the size of a grapefruit. She looked at it carefully and she found it was a black stone covered with frost. Well, I submit to you, in the south of France, on the 14th of May, 1864, now the 15th of May, early in the morning, you wouldn't expect to find frost on a rock. It's much, much too warm. What had happened was the piece of the meteorite had come through the atmosphere, and as it fell through the atmosphere, a part of it melted. It formed a fusion crust of about 1 millimeter thickness, but the interior had been soaked in the cold of deep space. And that interior remained cold, and then there was a thermodynamic battle after the meteorite had landed. The thin wall of hot material was quickly outnumbered by the thick regime of very cold, and the surface was solidified up very high in the atmosphere. Then it cooled down to the point that ultimately it reached the dew point, water condensed on it, and then as it went below the freezing point, that water froze into a layer of frost, which is very important because that means that in these carbonaceous meteorites, low-density carbonaceous meteorites, as they come through the atmosphere, if in fact there is any biology alive in the ices, it could easily be transported into oceans or lakes, and once the ice melts, it could indeed emerge into the aqueous environments and take up life on the planet Earth. The parent body of the Orgay meteorite, based on the trajectory, is thought to be a comet, probably a Halley type or Jupiter family of comets, and it's been shown that liquid water existed on the parent body as recently as 10 million years ago. Martins has shown that there exist amino acids in the meteorite, and by isotopes of carbon, she was able to show that del 13C of carbon of the uracil was plus 44, and xanthine plus 37 in Murchison. The soil was minus 10 and minus 15. Clearly these nucleobases, uracil and thymine, were not terrestrial contaminants. They were clearly extraterrestrial. The fascinating thing is that cytosine degrades to uracil with a half-life of 17,000 years. Thymine degrades to xanthine with a half-life of 0 C and pH 7 of 1.3 million years. Clearly, the absence of cytosine and thymine means that whatever biology was present in the meteorite had to have perished many half-lives longer than the half-life of thymine, otherwise thymine would still be present. So that suggests that the biology in the carbonaceous meteorites probably died tens of millions to hundreds of millions or perhaps even billions of years ago. It also shows that the meteorites are not contaminated by modern biology. Well, after David McKay announced the discovery of possible nanofossils in the Mars meteorite, and there was President Clinton making a big announcement, we thought, this is crazy. Everybody knows there are microfossils in meteorites. I had known that since the early 1960s. The only problem was I didn't know that everybody had concluded that all that earlier work was nonsense. So when they made a big deal about it, I decided, well, golly, maybe there aren't microfossils in meteorites. Maybe I've been wrong all of this time. So I decided, since we had a wonderful scanning electron microscope, this antique beast here, which was nice at the time, that was 1996, but since we had this scanning electron microscope called an environmental scanning electron microscope, and I was working at NASA, and I had the opportunity to know the people that ran the microscope, but when I told them I wanted to look for microfossils in a meteorite, they said, where? When? They were just as excited as I was. Well, I had ordered a 1 gram piece of the Murchison meteorite from a famous meteorite dealer, and I paid $100 for a little teeny rock about like that. And we started looking at it. My approach was, since they had criticized David McKay's results because they were coated with gold, they said, what he's looking at, these little nanofossils, this is his Mars worm, and this is clearly very, very small. I do not believe that these are individual cells, although he thought that indicated a chain of cells, but it's so tiny. I don't think that was the case. I'm not sure that the nanofossils that David McKay announced for the Alamitos meteorite were in fact biological. Except there were other things just other than the fossils. There was the polycyclic aromatic hydrocarbons and the magnetites and a whole host of other things that taken together indicated that it could have been biology. But that was not my problem. I knew that they had criticized him for having coating artifacts, and I knew that, well, if you don't coat, no one can criticize you for having coating artifacts. If you don't allow things to come in contact with water, no one can criticize for contaminants that were brought into the meteorite research. So my technique has always been very simple. I take a piece of the meteorite under very precise conditions with gloves and so forth, and I flame sterilize all my tools and so forth. I then use a small chisel and break the rock, and we're very careful to observe which surface is freshly broken, and then put it on the scanning electron microscope stuff and just look. Nothing else. No coating, no water, no aqueous environment. Just look. And when I started doing this, I immediately started finding microfossils. I wrote a paper and sent it to David McKay, and David McKay says, you know, he says, the Russians are doing the same thing. I said, what? He said, yes. He said, I have a paper from a gentleman by the name of Alexei Rozanov. Well, I didn't know who Alexei Rozanov was, that young guy. It turns out that Alexei was director of the Paleontological Institute for the Russian Academy of Sciences in Moscow. Alexei had this beautiful collection of tarbosaurs, all kinds of magnificent dinosaurs, and yet he loved bacterial paleontology. He's one of the fathers of bacterial paleontology. When a lot of people ask him, wait, you got these dinosaurs, why do you study bacteria instead of dinosaurs? He says, oh, dinosaurs, he says, they're much too big, much too heavy, and far, far, far too young. So he likes bacteria, and I like bacteria. And I asked David if he would send me Alexei's paper. He said, no, he's not even in peer review. He sent it to me for comment. I said, well, could you contact him and see if it would be okay for you to send him my paper? And he said, of course. And so he sent Alexei my paper, and Alexei then communicated that it was okay for him to send me his paper. And it turned out we had found very, very similar kinds of things in the same meteorite. So I started a collaboration with Alexei Rozanov, and then we established an astrobiology group at the Joint Institute of Nuclear Research, and here is one of the students who got his doctorate in astrobiology, Mikhail Smisha, and their instrument is different than the one that we use at NASA now, this Tescan 3 Triglab. That beautiful scanning electron microscope, again, doesn't require coating. The one in Russia and Dubna, you do have to coat with gold, but this is not important now because I know these are not coating artifacts, and so I don't mind having the samples gold coated. During the years, starting in 1996, we've studied this array of meteorites. In fact, there are several others that we've indicated are not on. This is an old chart, but basically, we're seeing microfossils in all of the carbonaceous chondrites, from CI, C2, CM2, CR, CO3, and CV3s. And I've looked at many different kinds of iron meteorites, stony chondrites, diogenites, and so forth. And for the 20 20 meteorites that we collected from Antarctica, and none of them were found to contain microfossils. This is the Murchison meteorite that fell at 10:59 on the 18th of September 1969 in Australia. It's a CM2 carbonaceous meteorite, and you see all these beautiful little chondrules. It's totally different than the Orgueil meteorite. Magnetites show a uranium-lead age of the order of 4.56 billion years, a cosmic exposure age of 800,000 years, but it contains pre-solar diamonds, pre-solar silicon carbide grains, a whole host of particulates that range anywhere from 6 to 10 billion years in age. The fascinating thing about terrestrial life, it prefers carbon-12 over carbon-13, and so you get fractionation in living things, of biological fractionation of stable isotopes, and this shows how you can go all the way down. Fractionation of isotopes was the late Eric Galimov. Eric Galimov was the distinguished director of the Vernadsky Institute of Geochemistry and Cosmochemistry. I had the good fortune to become very good friends with academician Galimov over the years. And it was only after we discovered diatoms and Orgueil that he finally said, well, okay, now I'm convinced there really are microfossils in meteorites. But when I first visited him and showed him my pictures, he said, well, you know, he said, there's something that's been bothering me about meteorites. And he showed me, pulled a book off his shelf, and he showed the biological fractionation in chlorella granuliosa, and gracilaria, and euglena. And here is his value of del sigma 13C against beta sigma 13C. And then he has the same plot showing the same kind of relative abundance of the different amino acids, but going from about plus 45 to plus 20 in the Murchison meteorite. And in this book, the caption says it is a remarkable analogous relationship between the biological between the fractionation of amino acids that we see in the Murchison meteorite to those that we find in terrestrial biology. When I saw that, I said, that's the best chemical evidence I've seen for the existence of extraterrestrial life. And he leaned back and he said, yes, I guess I can see how you might interpret it that way. The book was Eric Galimov's book, Biological Fractionation of Stable Isotopes. So it was his own book, but he had been reluctant to interpret it that way. I had a good fortune. I went to Russia many times, and every time I went, I would take a copy of the book, which I would buy in America from a source that I had. I would take a copy of his book to give to him because he had no more. He had given all of his away. So after he gave me the first one that was autographed, I kept bringing him books back so that he could have books to give to other visitors. The branched chain hydrocarbons are found in the meteorites, pristane and phytane, which come from the phytol chain of chlorophyll. You also find vanadium porphyrins, which are from the magnesium porphin in the head of the chlorophyll molecule. Pristane, phytane, and vanadium porphyrins are not modern biological materials. They are the result of ancient biogeochemical degradation of chlorophyll. But chlorophyll is not an abiotic chemical. This is one of the first images that I took. That is a visible light picture showing this very big structure. That's a 20 micron bar. And you can see here a structure in Murchison, in which you have a multiseriate filament here and here, and then this tapered filament. But the fascinating point here is 2D X-ray maps show this is high in carbon, comparatively low in oxygen compared to this phyllosilicate cap, low in iron compared to the rest of the meteorite rock. But the important point is the nickel and the sulfur. You see basically the same amount of nickel in the meteorite fossil as you see in the rock matrix, and the same is true of sulfur. If this was a modern contaminant, the nickel map should look just like the iron map, but it doesn't. So again, 2D X-ray maps from energy dispersive X-ray spectroscopy showing that it is not modern biological contaminant. This is a beautiful filament in the Murchison meteorite showing an escaped harmagonium, a hollow sheath here, and here we can see cross-wall constrictions making it possible to identify the size and shape of the cells. And here we see what are coiling harmagonia with the tail of the harmagonia sticking up just like a rattlesnake. This is characteristic of Gnosticacean cyanobacteria. This was identified by Georgi Zavarzin, one of the world's leading authorities on cyanobacteria. And when I mentioned, he asked why I was interested, he said, Gnosticacean cyanobacteria are common, they're found all over the earth. I said, yes, but that's in a fractured piece of the Murchison meteorite. Zavarzin says, well, that's deadly. And then he held the photograph and looked at it for about 3 minutes and put it down and said, that is Gnosticacean cyanobacteria. Sorry. And this shows the 2D X-ray map of this harmagonium, and you see the absence of nitrogen. The absence of nitrogen is very, very important because modern biology contains nitrogen, and the absence of nitrogen proves that these filaments are not modern biological contaminants. These are Murchison filaments, living cyanobacteria. These are contaminated. They were contaminated by a fungus in a sample that Meenakshi Bhatta of the Field Museum sent me. I called her and asked her how the sample was stored. She said in a box. I said, in a box? She said, yes, in a museum or in a box. And I said, you didn't protect it from contamination? No, why would we do that? It's just a rock. Well, the problem is meteoriticists consider these things just rocks. But, in point of fact, these are living cyanobacteria, and these are mummies and woolly mammoth hair, and again, trilobites. Well, the trilobites and the ancient cyanobacteria have no detectable nitrogen. The mummies, like the one we see here that I collected in North Siberia on an expedition with David Yolachinsky, we see a beautiful nitrogen peak that can be seen right there. The nitrogen in that filament of that hair of a Pleistocene woolly mammoth is around 11.6%. And I submit to you that this is not a modern woolly mammoth. So I'm convinced it died somewhere of the order of 32,000 years ago because we just don't have any modern woolly mammoths. Here I'm taking a piece of the Orgay meteorite, and you can see it here being moved around, and I am about ready to make a drop of water onto this tiny fragment of meteorite. There went a drop of water. And what is fascinating is that you see it's like an Alka-Seltzer tablet. All of these bubbles start coming out the instant the water hit it. This is video in real time. And you see a piece of Orgay starting to lift off there. Literally, the meteorite is disintegrating. That is very important because cyanobacteria and diatoms are aquatic microorganisms. Any piece of Orgay that landed in a lake or a river or was rained on after it fell would no longer be a piece of the Orgay meteorite. It would instead be a pile of black dust that would not be identifiable as a piece of a meteorite at all. This is an artist's illustration of what Orgay looked like when it fell. I thought I'd show you some magnetites. There are stacks of platelets of magnetites in the Orgay meteorite we see here, and also in the Tagish Lake. These are Orgay. This is Tagish Lake. Some beautiful minerals. These are framboidal magnetites that are found in Tagish Lake. One of the fascinating things is there's a lot of studies that indicate that framboidal magnetites are made by biology. They're found typically in clays, and so this is a biomarker, even though there are ways that you can make framboidal magnetites by non-biological processes. The most abundant form of framboidal magnetites on Earth are probably formed by biology. In 1967, Tan and Van Landingham published this image in which they show, this is the transmission electron microscope, one of the things they found in Orgay, and they said that it had a chain of electron-dense solid bodies that goes along here and down along here, and a big electron-dense region here. Well, they published that paper in 1967 and had no idea what they were looking at, because in 1967, no one on the planet Earth knew what a magnetotactic bacterium looked like. And there they have a magnetotactic bacterium. And here is the magnetotactic bacterium showing magnetosomes in Pseudomonas rutilis, a purple sulfur magnetotactic bacteria. That was given to me by Weinstein in 1997. And so here we saw a picture. There were actually several of these that Dan and Van Lanning had published, but they didn't know what they were looking at. This is one of my early pictures showing a very nice sheath. Whoops, I won't get in the way. Showing a very nice sheath with these individual cells within the sheath. And so we can tell that they're 2.5 by 7.5 microns within the sheath, similar to what you have in Cyanobacteria libia. This is very interesting because many of the cyanobacteria do fixation of nitrogen. Nitrogen in the atmosphere is an N2 with a very strong triple bond. You can't break it apart by simple fire, by simple chemical reactions. The way in which the N2 nitrogen of the atmosphere is rendered into amines and ammonia and nitrates and nitrites is by nitrogen-fixing bacteria. And the cyanobacteria, particularly the members of the Ribularian cyanobacteria, this is Calothrix. Many of these have these structures called heterocysts or heterocytes. One of the problems with nitrogen fixation is that the enzymes that do nitrogen fixation are poisoned by oxygen. And when you carry out nitrogen fixation and you carry out this kind of metabolism within the cyanobacteria, it's also doing carbon fixation and it's producing oxygen. So basically, the cyanobacteria isolates the oxygen, the nitrogenase enzymes in this thick, hard structure so that it can carry out the nitrogen fixation without it being poisoned by oxygen. And then as the material goes up, the filament has a tendency to become thinner and thinner, so you get tapered filaments in Calothrix and the other Ribularian cyanobacteria. This is like formidium, but one of the fascinating things here is we have two cells that are actually escaping here. Here is an escaped armagonium here. Again, these are filaments within the Orgay CI1 meteorite. This is clearly a cyanobacteria mat within Orgay. And here is an interesting form because this has all the appearance of being an escaped armagonium. And that escaped armagonium is in a filament here with a thick sheet. And when we do the EDX analysis, we don't see significant levels of carbon. It's been totally replaced by magnesium sulfate. So clearly this is not a modern biological contaminant. Again, very complicated cyanobacteria here with an apical hair with a delaminated part of the sheath. And when we do the spot right here, we see carbon at 82%, oxygen at 9%, an oxygen-carbon ratio of 0.11, kind of like what you'd expect from fairly highly matured forms of coal. Certainly not what you would expect from living biology. These are Lophotrichus tufts of fimbriae. When Rosemary Ripka Herdman saw these, she started talking about how she'd never seen Lophotrichus tufts of fimbriae look like this. I didn't know what a Lophotrichus tuft of a fimbriae was. So she kindly explained it to me that they're quite common in many of the bacteria, including the oscillatory and cyanobacteria. But she said she had never seen them except in TEM images, and here these guys are standing up in free space, and that's a 200 nanometer bar. So those are about 30 or 40 nanometers in thickness. The only way you can explain that picture is these cyanobacteria were living inside a pool of water near the crust of a body like a comet, and an impact caused a fracture of the crust, and the water immediately evaporated into the 10 to the minus 10 to the minus 12 pressure of space, and all the predators died at the same time the cyanobacteria died, and you have these filaments remaining. Some people claim you can't recognize life by morphology alone. Well, you can't tell that to a diatomist, because for over 2 centuries, well, in fact, a cyanobacteriologist either, for over 2 centuries, morphology has been the mechanism for characterizing the genera and species of cyanobacteria and diatoms. In 2017, we had our first discovery at JINR of recognizable diatoms in a carbonaceous meteorite, in Orgay, I should say. We found lots of them in Poland, but in Orgay, there we see a diatom with the same characteristics of Pinularia sigariana, which was found by Neil Fogan, described first by Fogan, and this particular Pinularia sigariana was from New Zealand, and it had been found much more recently than Fogan's original work. But New Zealand and the south of France are very, very distantly apart. These are more cyanobacteria in Orgay, including one of the things that's nice about this one. You can see where the top of the diatom comes up here, and it's clearly embedded in the rock matrix. Again, 13 by 0.3 by 5.3 microns in size. This is a small pinnate diatom. All the diatoms that I've found in the Orgay meteorite have been very small pinnates. This is a 13 to 14 by 3.8 to 4.5, possibly Stauronesis nana. Several of these diatoms are very clearly beautiful fragments like this, but have not yet been precisely identified. Another fragment of a diatom with elongate puncti. And sometimes in Orgay you find really bizarre stuff. This is absolutely amazing. I have no idea what it is. If anyone has ever seen anything like this, I'd like to know what it is. But here's the fascinating thing. You see it as one filament coming off here, and then this big major filament. That's chlorine map. And here is the fluorine map. Chlorine and fluorine. 30-something% fluorine. No, that's not like most biology that you encounter, and yet this is an enlargement of that central area. And if that is not biological looking, but also incredibly bizarre looking, I have no idea what it is. I would love to know if there's an analog to that in any life form on Earth. In 2012, the Polonnaruwa stones fell in north central Sri Lanka. This guy, Tigiri Banda, burned his right hand when he picked up a piece right after it landed. I was giving an interview with Sri Lankan television, and I looked, and about 2 meters away, this stone was lying on the ground. I went over with aluminum foil, sterile aluminum foil. I carefully lifted it up and immediately put it right back down, because it was like I was lifting a piece of styrofoam. The density is so low that this will float on water. And the fascinating thing is that we've got analysis at the University of Cardiff, cristobalite, hercinite, anorthite, wustite, albite are found in it. We see in this ilmenite grains, phaolite, olivines, quartz, zircons, the high pressure polymorphs of olivine like watzleite and maskelinite. And the fascinating thing is, notice this ilmenite, you see, and here enormous amounts of fracturing. This, of course, is a 200 micron bar, and here's maskelinite. That forms at pressures of the order of 20 gigapascals. You find that deep in the crust of the Earth. You find it in bodies that have been involved in asteroidal collisions. You don't find maskelinite in rocks lying on the top of the Earth in a rice paddy field. The laser fluorination technique was used to measure triple oxygen isotopes in the meteorite, and we had the 2 world experts, Andreas Mach and Aiso Nakamura, make the measurements. They got Dello 17 values minus 0.296 to minus 0.335 in very good agreement. One done in Germany, the other one done at Okayama University, University of Göttingen in Okinawa. So they were in good agreement. But the fascinating thing is that all rocks on the Earth and Moon lie on the terrestrial fractionation line. The CI1 carbonaceous chondrites are up here, and the polymer stones are down there. So their oxygen isotopes are clearly indicative of extraterrestrial rocks. Kerogen is seen here, but that again, that's the interior. I know of nothing that looks like that. I showed it to scientists at the Colorado Botanical Institute in St. Petersburg, and when they saw it, I had marine biologists, microbiologists, and the director, and I asked him what it was. He said, something biological. I said, yes, I think it's biological. I said, what kind of life form were we looking at? Acrotarch, were we looking at dinoflagellate? What kind? Something biological. And that was the extent of the classification that I got. I think these chains may represent sulfur bacteria. You can see vibrions along here, very similar to the sulfur bacteria that we've studied. Again, something biological. I do not think this is a diatom, but I have no idea what kind of creature that may be. This, I think, may be a stratosphere, but amazingly, you see here these gigantic spines. Now, this is a 100 micron bar, and this spine keeps going all the way out here to around 150 microns, and it's about 8 microns in thickness. Kind of spines like that you don't expect to find in any kind of fossil deposit ever. They would be so fragile, and yet there it sits in all of its glory and we see it has a very high concentration of carbon and aluminum. It is deficient in nitrogen. I love these diatoms because these are in Polymerua, and these are Alcocera ambigua. This is a long chain coming right out of the rock makers. Never seen chains of diatoms like that in any fossil deposit I've ever studied. And what is amazing, this is terrestrial Alcocera ambigua. This is an image right in here at higher magnification. You see the rim of portuli, you see the areolae, you see the cribra, you see the regalis, the separation spines. This is a 10 micron bar. I showed this to the World Authority on Alcocera ambigua, and she agreed the species and genus is correct. But she said she's never seen one that looks like that because of the state of preservation. Again, this is a strange diatom with square pores. These are all in Aralaganwilla, which is one of the Polymerua complex. This is an avicula that I collected on the day of January the 29th, 2013. I had it in my collection and put it on the electron microscope stuff. I actually didn't discover it until October 19, 2021 at the Paleontological Institute. But the fascinating thing is, notice these slits that come along here and go parallel to the rape at the central pore. And I was most excited about this diatom, and even more excited when I found this paper that was published by Chudiev of a new diatom, a new species that he named Navicula trophocatrixoides from the Voronezh region of Russia, and he published that paper in 2020. Well, I had the diatom in my possession since 2013. Of course, I didn't actually find it until after that, and if I had found it, I wouldn't have known that it was a new species of Navicula, because there are so many thousands of species of Navicula, and I'm not terribly an expert at the small pinnate. Water, we know, exists on comets. This is a picture of Comet Halley, and then the cliffs of Stardust image of Ville 2. Here is 67P Cherry Mouth Gerasimina, and here is a very beautiful set of images that have been put together showing snow on Cherry Mouth Gerasimina. And here we see the Sunshine et al. Paper on data obtained on Comet 9P Temple 1, and here is their video, which shows this enormous flaring of the comet, and that was out beyond the orbit of Mars. There was no reason for this flaring to be occurring unless it was becoming heated as it approached the inner part of the solar system, and regimes of gases like methane and carbon dioxide and water evaporated and produced pressure, causing fractures in the crust. and release of large quantities of liquid materials as well as dust from the crust. But the important point is here beyond the orbit of Mars, the temperature in this regime is 330 Kelvin, and what is shown in their paper is that this region, it goes down to about 280 Kelvin. Well, 280 Kelvin, 273 Kelvin, that's a magic number. That's the number where ice changes to water, 0 Celsius. For some reason, they didn't carry their chart on down to lower temperatures, but I'm submitting that this whole region in here was actually where you had a slush of water and ice. And up there, when the sun is shining on this jet black surface, you get the production of what's going on. You get production of water gases and other volatiles. I'm planning on going to Tbilisi, Georgia, where Professor Dr. Simonia did a wonderful paper in 2018, and they looked at unidentified spectral lines. This is just a fragment of the spectral lines that they were able to identify because they used a database not with simple organic chemicals like the kind of things that you get by Miller-Urey synthesis. They used a database which included biomolecules. And this whole suite of unidentified spectral lines, they identified with luciferase. And then there are some that identify with H-morphin and others that are identified with chlorophyll. Well, luciferase is there. That is not a simple biomolecule. You have 7 exons coding for 547 amino acids that span 1,976 base pairs of genomic DNA. That is biological. There is no way you can make luciferase by abiotic mechanisms. Asteroid Bennu has been shown to have some very strange things like this. This is Gargoyle Saxon with a bright carbonate spot on it. And when Rositas wrote their paper in 2020, they say the weaker boulder type probably would not survive atmospheric entry and thus may not be represented in our meteorite collections. Well, after the Polonara meteorite landed, we did calculations and we were able to show in a paper that we published in 2013, the incidence of low-density meteoroids of the Polonara type. We were able to show mathematically they could indeed survive transit through the Earth's atmosphere. Here is an image of a fragment of the Arlagimilla Polonara meteorite. Density is 0.6, porosity 80%. Very, very similar to this thing, which is a Bennu boulder. There also are bodies in the solar system. We have interstellar comets that actually travel through our own solar system at trajectories like this. That's Oumuamua. The transit time from Captain Star, which is only 7 light years away, at the velocity of Oumuamua would be 85,000 years. There are others like the interstellar comet 2I-Borisov, and we know that it was at Kruger 60, that star about 1 million years ago. The fascinating point is that rogue planets, maybe planets like the planet Earth, for example, if it was caused by a nearby passage of a star to be thrown out of its orbit and pass near the sun and then come out and get gravitational assist from gas giants like Saturn or Jupiter or Uranus or Neptune, it could achieve the 30,000 kilometer per second escape velocity. And with that kind of escape velocity, it could then travel to a nearby star system, or perhaps even a distant star system. But long before it did, the outer crust would have frozen over with water ices, and then with nitrogen and methane and carbon dioxide ices. But underneath those ices, you would have a liquid water ocean. And that liquid water ocean would be heated by serpentinization, and it would be heated by the deep rock heat-producing elements. And that liquid water ocean could remain liquid with all of the biology that is alive there, like the deep tube worms and the great, beautiful crinoids of the deep sea, and all of these other organisms that live in the very deep sea. They wouldn't really care that the sun was no longer anywhere nearby, and they could continue to live and replicate and die for another 4.5 billion years as they travel to a distant star system. And over that kind of time spans, they could indeed travel to an entirely different galaxy. So we're calling this mechanism wet panspermia, in which panspermia is not by cells thrown into space that would have to try to survive desiccation and radiation. Instead, it would be living biology that is replicating and growing inside of liquid water oceans, surrounded by an icy crust that maintains the water, keeps it from evaporating, and provides it with insulation, and the heat-producing elements and serpentinization provides it with energy to remain in liquid state and to support the biological system. So in conclusion, I conclude that there are problems with the current origin of life models, and I suggest that life on Earth may have been delivered to the early Earth, and maybe even much more recently, because we have a continuous influx of meteorites and cometary debris. The conditions for life, water, energy, and bioenergetic elements, coexist on every comet, planet, moon known of the solar system, and there's no reason to think that they would not also coexist on exoplanets and exoplanetary systems. Nitrogen levels prove that the cyanobacteria, acritarchs, and diatoms that I found in the meteorites, along with my colleagues in Russia and United Kingdom, are indigenous and extraterrestrial, and therefore the major conclusion, extraterrestrial life exists. Life on Earth may have formed on comets and exoplanets more ancient than the Sun, and then transferred to Earth by interstellar comets or rogue planets. And with that, I thank you for your attention.
Thank you. It was a pleasure to hear you. And please, comments, questions.
Our criticism. Our criticism. I welcome all comments. Yes.
Thank you very much for your amazing studies and presenting us these wonderful discoveries. I would like to ask you, because I am interested in possibility that some iron fractionation to be produced by iron oxidizing or iron reducing bacteria. And I would like to know your opinion about this kind of iron, biological iron fractionation produced by bacteria.
Yes, there is a large body of the microbial system in which you have both iron oxidizing and iron reducing bacteria. And one of the things that we see in these meteorites, as I showed, are magnetites, and also pyrite is a very, very common component of the carbonaceous meteorites. I firmly believe that the biological systems of sulfur and sulfate-reducing bacteria and iron reducing and iron oxidizing bacteria, as well as hydrogenotrophy and various other forms of chemolithotrophic microbial systems are probably very, very important to what we're finding in the carbonaceous meteorites. So I think that's a very, very fruitful realm. One of the other things I didn't touch on when I gave this presentation years ago in Hanya, Crete, Alexander Spirin was there, and Spirin had done enormous work on the RNA world. He came up afterwards and he said, "I hated your talk." I said, "You did?" He said, "Yes." I said, "If this is right, then the RNA world may not be right. Because in point of fact, the RNA world is the idea in which life began with RNA on an early planet, probably when you had a snowball Earth and so forth. But the basic point is, I don't agree with that, because life had to have originated somewhere and somewhen. I'm not saying that it did not originate by the kind of mechanisms that the theoreticians have been working on, but I'm saying that that origination probably took place over much longer time periods than 200-300 million years. So the only thing that I'm doing is saying it probably occurred, it had to occur somewhere, at some point in time. But I think the evidence is that that place was not on primordial Earth, that we got contaminated by biology from somewhere else. And I fully think that that contamination by biology probably is still occurring, because we continually fly through debris fields left off of meteorites, and those meteorites are actually garbage trucks. They come from deep space, from the Oort clouds, or from the Jupiter family of comets, and as they sweep inward, they pass through water jets that have been sprayed out of Europa and Enceladus, and they scoop up any kind of aquatic material and possibly even microorganisms that came out of the oceans of Europa and Enceladus, and material blasted off of Mars from the polar ice caps of Mars and the permafrost of Mars. So I think what's happening is things are continually exchanging biological material throughout the cosmos. And that may be the greatest secret of all, that life is just like the chemical elements, just like the laws of physics, the laws of biology and microbiology, molecular biology and biochemistry may be just as universal as the laws of physics and the laws of chemistry. Now, the fascinating point is that suggests that the life that we find on Mars may look just like the life that we find on Earth, or the life that Juice finds. Well, I don't really think Juice actually has the capability of really finding life, just saying, well, it could have been there, just like our Mars experiments have done. But I think that if we do find life on Mars, and it looks just like cyanobacteria and just like terrestrial biology, well, the scientific community will say, well, of course it does, we contaminated Mars. Well, the nice thing about these pristine sample return missions, like the returns of Bennu and Ryugu, is that they're not contaminated. But they found amino acids with an L excess in the samples returned from Ryugu. They didn't really mention it in the scientific paper, but when you look at the supplementary data, you see that there was a definitive L excess in some of the amino acids found. Again, an indication of biology, not abiotic chemistry.
Thank you. Please, more comments, remarks, questions?
Then we will just wait until we will see extraterrestrial life.
Please speak up.
More intelligent extraterrestrial life, no? Than architect. So it is possible to meet more intelligent life.
Intelligent life. Intelligent life, yes. We had an astrobiology conference at SPIE in San Diego in 1997, and we had a live video feed with the late Arthur C. Clarke. And a young 8-year-old boy came to the microphone and he asked Arthur Clarke, what do you think are the chances of finding intelligent life in the universe? And Arthur Clarke responded, he says, I'm very optimistic. It's my hope that someday we may find it on Earth. But actually, if we were to be transported into the past, 100 million years ago, we would see all kinds of biology, but we wouldn't, we would say, gee, there's a dinosaur. We would recognize it because we've had paleontologists. But if we were dumped back into the time of the Burgess Shale and we see Opabinia and Hallucigenia and all of the bizarre-looking things running around, we would think we've been transported to a different planet because those things don't look like they belong on Earth. So I think the one way that we will know that it is not contamination is by study of these pristine samples that are returned. But also, I firmly believe that we will encounter other truly bizarre and strange kinds of life. Maybe some that use different chemistries. Maybe some that work with D amino acids and L sugars rather than L amino acids and D sugars. If we were to find a biological system operating on exactly the alternate chirality, then I think that the scientific community would have no way to go but to say, that is clearly, undeniably extraterrestrial life. But as far as intelligence, well, we now know that there are all sorts of strange things that have been going on that our own Department of Defense has now started talking about, in which things have been imaged by aircraft and by radar, in which they've been seen coming from very, very high regimes of the stratosphere and descending to within 50 meters of the ocean surface and stopping abruptly and being chased by our best fighter jets and playing with them, taking off and moving at very high velocities. So there are some strange things. There are, I guess, stranger things that are dreamt up in our philosophies. I think someone said that. Like Shakespeare, I think it was. And so one of the things that we have to hope for is if there are intelligent extraterrestrials, that when they come here, they come in peace, like we should hope to do when we go to Europa and Enceladus and when we return to Mars. And I do think that we will return to Mars within the next decade, because Elon Musk has a starship that is capable of flying to Mars, and we are hoping to send a light detection experiment to Mars, because I'm convinced that Gilda Ben found evidence of biology on Mars in Viking. And since Viking, there has not been flown to Mars a single experiment capable of searching for life. We've had experiments to look for rocks, and we found rocks with great success. But finding the rocks on Mars is not nearly as exciting as finding biology on Mars. I apologize to the geologists. Finding rocks is very exciting, but finding biology is, to me, even more exciting. We have good reason to know there are rocks.
Produced by biology.
What?
For example, they are rocks produced by biology.
Absolutely, absolutely, absolutely. This whole geomicrobiology is a wonderful, wonderful field. Yes.
Thank you, please. More comments, more questions, more remarks? Okay, Richard, thank you very much. It was a real pleasure to have you with us.
Thank you. Thank you very much.
Thank you.